Okay, let me share here. And here is my favorite problem, the launching of a rocket. Okay, so if you read carefully what's happening in this problem, a rocket model is launched and there's a propellant that burns for a few seconds. Okay, then after that burns out, the rocket coasts and eventually it will start to fall, right? That's a basic principle of physics. What goes up must come down, right? So it will start to fall, but as it's falling, a parachute will open and kind of break the landing. So anyways, we are looking at a velocity graph. And remember how I talked about how confusing and how counterintuitive it is to look at a velocity graph. Because if I asked you, when does the rocket start falling? It's tempting to say, well, it was rising until we got to 2 seconds, then at 2 seconds it falls. Remember, we are looking at a velocity graph. So what we actually need to do here, and I'm going to select my line tool to help me, we actually need to look for where velocity is 0. Okay, because remember, when it comes to velocity, positive velocity means the object is rising, right? So we are rising all of these for all of these seconds up until we get to 8 seconds, right? Because velocity is positive. Okay, so the object rises and then changes directions at 8 seconds. Now, we also have to remember that acceleration is the slope of velocity. So if we came along our velocity curve and we drew some tangent lines, right, to represent the slope of the velocity, which would be the acceleration, one of the things asks you when the acceleration was the greatest. And this is where the engine is burning, right? So this propels the rocket upward. So right here where I just highlighted in red, we have positive velocity and then positive acceleration. That's where my rocket is speeding up. Okay, but then we get to 2 seconds, and now I have negative acceleration with positive velocity. Okay, so remember that if velocity is still positive, but acceleration is negative, that means my object, although it's still rising, right, because we rise all the way till 8 seconds, because that's where velocity is positive. In here from 2 to 8, from 2 seconds to 8 seconds, we actually are slowing down, although we're rising. So that's where it's coasting. It's still rising, but it's coasting. Okay, whereas from 0 to 2 seconds, it was accelerating because of this engine that was burning, right? That propellant. So let's start asking or answering some of the questions. So for how fast was the rocket climbing when the engine stopped? Okay, so the engine is referring to this propellant, right? So how fast was it going? How fast means the speed. Speed is the absolute value of velocity. So it appears here that if we looked across at 2 seconds, and for how many seconds did the engine burn? So that answer is 2. Okay, and then how fast was it going? So if we look over here, for speed, we take the absolute value of velocity, well, it was positive anyway, and then don't forget to include feet per second. Okay, so then let's come down below. So I might do these questions out of order because let's focus on the questions then we've already answered. Because first of all, it's talking about down here. Well, actually, let's do C. When did the rocket reach its highest point? Again, it's so tempting to say, oh, right here at 2 seconds, we're at the highest point. No, that's when we went from speeding up to slowing down while it was still rising. That's not when it reached the highest point. The highest point that it would reach is right before it changes directions. Okay, so this would be t equals 8. So again, looking at a graph of velocity, it's so counterintuitive. But our highest point was reached at t equals 8. And remember, at the maximum height, velocity is 0. Okay, so let's see, let's do F and G next, because we've been talking about the acceleration. Okay, when is the rocket's acceleration the greatest? So, you know, we look at the slopes along this curve, and where is the slope the steepest? And notice how steep these are, and it's steepest, I think the answer key says an exact 2 seconds. I don't really want to, I wouldn't call it an exact 2 seconds. I would call it just before, right? Just before 2 seconds. Because if 2 seconds is when we had that change, when the engine stopped burning. So just before 2 seconds is where that slope is the steepest, right up in here. Okay. When is the acceleration constant? Okay. So again, when again, acceleration is the slope of velocity. Okay, so where does the velocity have a constant slope? And we see that from 2 seconds till this whole part where the velocity is linear, right? That's where it has a constant slope. So that's where acceleration is constant. And they call this 10.8 seconds on the answer key. It's a little hard to be precise looking at that grid, but they call that 10.8 seconds. So through this region, it is constant. Okay, and then it wants to know, well, what is the acceleration? Okay, so you've got a linear function. Let's find the slope of it. So to find the slope of a linear function, let's pick some points that we know are on there. For example, I know the point 8, 0 is there, right? Because that's where it changes direction. And then I know the point, so at 2 seconds, and it's not perfect. That's why I'm not going to get an answer that's perfect. So at 2 seconds, we have a velocity of 190, I said. Okay, so if we go to find the slope, this minus this, so I get negative 190. And then, so that's change in y divided by change in x. So this would be a positive 6. Okay, so I'm going to divide this by a positive 6. And notice that I get 30. And then I'm going to get 1. And then I get 4. So I get 31 and 4 over 6, which is 2/3, which is 31.6 repeating. Technically, okay. But what I should be getting, because this is the constant of acceleration on Earth, I should be getting an even. So that's why these points aren't perfect, because I should be getting negative 32 feet. And remember your units for acceleration. Units are seconds squared. So negative 32 feet per second squared. Because that is the constant of acceleration anytime an object in Earth is in free fall. So then let's look at the part down here where the object is falling. Okay, so anywhere velocity is negative, right? Down in here we are falling. Okay, so what happens at first is that because velocity is negative and acceleration is negative, and we know this when an object is falling and it's in free fall, it's speeding up, right, as it falls. I mean, that's due to the gravity acting on the object, pulling it down towards the Earth. That's what happens. So the object is actually speeding up. But then here, when we have velocity still negative, but acceleration positive, okay, so we know anytime these signs are opposite each other for velocity and acceleration, we know that that means the object is slowing down. Okay, so what is causing it to fall at a slower rate? That would have to be the opening of the parachute. Okay, so when did the parachute open? Wait, how long did the rocket fall before the parachute opened? So it started falling at 8 and we call this 10.8. All right, so that would be 2.8 seconds. Didn't leave myself room to write the answers. Okay, so 2.8 seconds. And when did the parachute pop out? Okay, so we're kind of going out of order here because it fell for 2.8 seconds until we got to 10.8. So 10.8 is when it popped out. Seconds, again, I should be labeling. And then it said, how fast was the rocket going then? So if I look across, remember, how fast is speed? Speed is the absolute value of velocity, right? So look across, velocity appears to be about -90 feet per second, but we can answer that with a positive, right? Because how fast is referring to speed. So it was going 90 feet per second. So as I said, this is one of my favorite problems because it gives you, it's not like the two that are up above here, right? Where there's no context and you're like, well, what would make an object move like that? I don't know, right? So there's no context up here. But I like this one because then, we can see all the reasons and put our common sense and logic together with what we see on the graph. So thanks for watching, and I hope you liked this problem as much as I did.